On this episode of the Rankled Engineer Podcast, Tim returns as the overload of pronunciation, and if you don't say this word incorrectly, I guarantee you work with somebody who does. We're going to take a look at crash bollards and barriers, and many of the design mistakes and methodologies that are incorrect, and so you're going to want to listen to this discussion. And I recently just finished an engine swap in my Mazda 3 from a 2.3 liter to a 2.5 liter motor. Welcome to the Rankled Engineer Podcast. I'm Gates. I'm here again with Tim. We've got some fun stuff, I think, today, a topic we both have dealt with a lot. Before we get going, the overlord of pronunciation, Tim, he's got a word for us this week. And do I want to say it?
I'm excited about this one.
Yes, so it's eccentricity or eccentricity, or what is it, Tim?
It's eccentricity.
Okay.
The first EC comes from ecto, from outside of. It's eccentric. So yeah, eccentricity.
Yes. So I hear it both ways all the time. I'm probably I'm a 60-40 eccentricity kind of person.
Stop it.
I try to. It's and for those non-engineers, it's basically just when you're dealing with a load, how far off center is it, is normally what we use that term for. And so it gets used a lot when we're considering that in our designs. But thank you for setting the record straight. So we wanted to talk about crash bollards today, but specifically rated crash bollards. And this is a pretty interesting topic in that it has a lot of defining criteria you have to understand. It really
came about when 9/11 happened, don't you think?
So I think
that's when everybody started hearing about them.
Right. And I think that's when the confusion really stepped in, because it became ubiquitous for people to need crash bollards. And I kind of divided as I was looking at the history of this and what we do today for bollards. I broke it into 3 or 4 categories where you have a need to control a vehicle with a physical barrier. One is security for an installation like the DoD uses, which is the genesis of the need for bollards, is the DoD protecting their assets. We use them as a psychological deterrent to get people to move their cars or vehicles how we want them to, so kind of traffic flow, or to keep them from running over a thing, even though that bollard may not be strong enough to stop the vehicle, but it's a visual barrier that you go, oh, I don't want to hit that. And then we also use them for like liability, loss of property. We put them all the time around garage door openings and the trash bins that, when we don't want to hit the wall, we'd rather hit a bollard because it's cheaper to replace a bollard than a wall.
Yep. And they go way back. I mean, you'll see them from buildings that are well over 100 years old that have them on either side of the entrance to a portal that you drive through into a courtyard or something like that.
And then you mentioned 9/11, and to me, this is where the confusion kind of lied. Before that, you had traffic barriers, you had DoD rated barriers, and then you had the psychological, the fake ones, right? The ones that just look like
accidental or incidental, that kind of thing, but none of it had to do with intent.
Right. And so 9/11, and it even goes back further than 9/11, I'd say the Trade Center bombing in 93. Right. The need to keep certain vehicles away or set back from your buildings. That started the process. 9/11 accelerated it, where we said, hey, we've got lots of buildings that are vulnerable at street level. What are we doing to keep vehicles from just hopping a curb and driving into a lobby or adjacent to a building column?
Or how do we keep vehicles out of pedestrian promenades and that sort of thing, areas where people could get in the news basically by switching from a vehicular area to a crowded area?
Yep. And so that's, in the last 10 years, we started to see vehicles not used to transport weapons, but to be the weapon. And so that's another, how do we keep those vehicles separated from pedestrians? And it's a difficult task because typically those who are making the decision that it's needed aren't special. They're not engineers. They're not security specialists. They just know there's a hazard that they want to mitigate. And if you type in crash rated bollard or crash protection or any of those types of things, you get a variety of information on what's acceptable and what's not. The one with the longest history, as we said, is the DoD and their testing and their K ratings of bollards. That's, in walls. The difficulty is what the DoD is trying to accomplish with that crash barrier is usually completely different than what our clients and owners are trying to mitigate with the crash barrier. And the DoD uses setbacks from their building to determine how far a vehicle's payload, not the vehicle, but the vehicle's payload, can incur past the perimeter. So if you have a building that's 100 feet away, they allow that vehicle to incur further into the perimeter than if that vehicle's only 10 feet, or the road's 10 feet from the structure. And different truck weights, different velocities of the vehicle, but it's all about penetration of the payload. And so when you think of a truck that has 10 foot long cab, and then the payload, and the strictest criteria is that 1 meter penetration, 3.3 feet, right? That means the entire cab of the truck incurs past the bollard, and the payload is allowed to go 3.3 feet past the bollard.
Right.
Does that do a lot of good against a pedestrian who's on a sidewalk 3 feet away?
No. And from that standpoint, when they talk about risk mitigation, unfortunately, as it works in engineering, it comes down to how many people are we trying to protect here? 100 or 1? There's a difference.
Yes.
Especially when you're trying to create a perimeter that may be hundreds of yards long or more. Certain costs are just untenable.
Yep.
And you can't make a barrier that's absolute. It's too expensive. It's like you might as well be building out of solid gold. It just becomes too expensive.
Yeah.
So you have to ask how is the risk being defined?
And the easy solution is to have lots of property and be able to clearly separate pedestrians from
possibly
traffic.
Can. Yeah. Space is your friend.
Yeah. But in urban environments or malls or things like that, you just can't get the vehicles far enough away from a barrier and the people
and every person.
Yeah. To justify the DoD rating. Now, like I said, it's the most established. It's got the most products that are rated by the DoD. The testing is very clear. There are testing labs that will do it all over the country. It's an easy process. But it's not giving the owners what they think they're asking for, or what they're asking, what they think they want. They ask for a DoD rated bollard because that's what everything out there is. The closest other code is going to be AASHTO. So your highway design guide has traffic control measures, things like in parking garages, on the 5th floor, you don't want a vehicle to go over the barrier and fall 60 feet down to the ground. So there's load criteria for how to design that. But that's accidental impact, right? That's somebody right. Who's just not paying attention. That's not somebody who's got a hammer down on the accelerator. Or when you're on the highway, there's all kinds of barriers and ways to, I call them directing barriers, right? To direct a car that is off course back onto the road.
Like a pinball machine where you're basically trying to send it a specific vector.
And AASHTO gives you a 15-degree impact, which is a glancing impact, which means the out-of-plane vector on the wall is much less than a head-on collision.
Right.
So we have this problem. Everybody wants to stop the vehicle cold, dead, no incursion into the space. But there's really no way to design that. And there's really no qualifications that exist to where you can specify a product that meets that requirement.
Nope.
So what do we do? What's the solution here?
And because it's so poorly documented, structural engineers are left to figure out solutions, and they don't necessarily have the best information because what book do I go to, what code do I go to, what approach do I use, do I use an equivalent static force approach, because that's really inappropriate for this type of design, where you're expecting everything to get destroyed. Your stuff, their vehicle, all of it's going to get smashed, and that has no relation to equivalent static design.
So I absolutely want to talk about some of the ways we've seen of dealing with this. Before we get there, I'm going to make the statement that if you're an engineer and you're designing a bollard for crash resistance, you're doing it wrong. That is the incorrect way to do crash rating. With one caveat. So, and the DoD leaves it open for this, even though they don't tell you how to do it. If you're using ANSYS or a very high level FEA program that is capable of doing the kind of analysis that's really occurring, I bow down before you. And yes, absolutely keep doing what you do. And I know a couple firms that they do this. One firm that I found out about, they do simulations of car crashes. And they got into the other side of that equation because they had to build objects for these cars to run into. So once you have the forces for the cars, you have the forces for the object it's hitting. But that's not what 99% of us structural engineers deal with. We don't know how to do that kind of analysis. We're not material scientists, and we don't have that high order understanding of, we're beyond elastic and we're well into inelastic properties
and
of
even
thousands
the
of parts.
soil, the foundations, that kind of thing. You're looking at the dynamic friction in post shear failed foundations. It's like, what, we have no training or basis for that as traditional structural engineering practice.
And so the as you said, we can make this an equivalent lateral force type of problem, right? I know how much the car weighs, I know how fast it's going, and I can look at video and see how quickly it slows down.
Right.
And I can do F equals MA, and I can figure out what that load is if it were a static force on my object. The difficulty with that, it's huge. And the stiffer you make your immovable object, the worse that force becomes, because there's not the rebound. You're relying on the car's crumple zones more than anything to dissipate force.
What degree of resistance are we looking at also? You're looking at the steel to fail just as much as an LRFD beam fails? Because, there's a lot more energy absorbing capability in there.
Yep. And as we know with our stress strain curve, we live in this happy short area.
A little bit.
As structural engineers. And we all took our material science classes and we talked about that nice curve where energy is absorbed and the toughness of the material is considered, but we don't know jack about it.
We never talked about using it.
Yeah,
we just said it's there.
Yeah, so, and I always get tripped up by, what's your soil doing? Because to me, the impact's not linear. The force is not statically equivalent over that 0.002 seconds, right? It spikes and drops quickly. So your max is not near your mean.
No.
So, what happens if you mobilize everything or you just shear that bollard off in the first quarter of the impact and you were relying on the full impact to dissipate that energy? You're out of luck.
Right. And you're not close either. You're off by orders of magnitude. So it's not the kind of thing where you can say good enough, because you're nowhere near good enough.
And if you happen to design it this way, you end up with a hugely expensive design. It's awful. And then you go look at what the manufacturers have out there that's tested, and it's a quarter your size, and the foundations are much smaller, and you're like, the math doesn't equal the reality. And no, it doesn't. Because we're not doing the right kind of math.
Correct.
And we get away with it in seismic and to a lesser extent the need in wind, because those are dynamic loads, but they're relatively long periods. The load swells and drops. It is a type of impulse load, but it's not an impulse load like a blast or a crash.
Right.
We've now, again, orders of magnitude, right? We've changed the impulse load by orders of magnitude and expect that our standard statics physics is supposed to work. No, please stop. The most egregious error I saw was an engineer who took a tested bollard and then did the calcs for it. and passed it off as their own. And they used, to design the foundation, a restrained embedded post in the ground. Because, it was up against a 4-inch concrete slab in the middle of this walkway.
Okay.
The analysis said there was something like 80 or 100 kips of lateral resistance at the ground level to keep the bollard from moving. Wasn't tied with any kind of steel to the area development slab. Wasn't tied with any mechanism to develop that load, and let alone the slab didn't weigh anywhere near enough or have the physical strength to, it's turning into dust at that point.
Right.
Gravel is flying all over the place.
It just pulverizes. Yeah, exactly.
You can't. Is it slowing the vehicle down? Absolutely. And that's what we're looking for. We're looking for heat. We're looking for things to move. We're looking for things to bend. But you can't design like you do for dead and live load. It doesn't work. So stop doing it. Use a rated bollard and explain to your client when they ask for the impossible that says you've got a couple avenues here. You fall on the DoD spec and you follow that to the letter and get a tested product. Or you put what feels good as a deterrent, but understanding that it's really not going to, you're never going to stop a vehicle from incurring past a bollard if there's somebody right next to that bollard. It's impossible to stop. And we've seen the videos of accidental vehicles that hit bollards, and they don't stop dead unless it's a small vehicle. There was a bus in LA, 3 or 4 years ago, that slammed on its brakes and lost control and did a 90, but was still moving 30 or 40 miles an hour, and it blew through the Jersey barrier between the opposing traffic. Because that barrier doesn't stand a chance with a 90-degree impact with a vehicle that weighs 20 tons. And I've been in warehouses where I've seen, because of how rigid forklifts are, at 3 miles an hour, they will rip a column in half by just bumping into it. They weigh a lot, and they're half-inch plate steel, and they don't bend. They don't have a crumple zone. You can't fight, those kinds of instantaneous loads with conventional means. Any thoughts?
Well,
I try not to be too mean, but it does bother me a lot.
So, and then the next thing is getting into the analysis. So you have to look at, where is the vehicle coming from? How much room does it have to get up to speed? Because you can potentially limit or be subject to high speeds depending on the geometry of the approach.
Yep.
And then you have to look at the friction of the tires and the car's ability to make a turn, because another point of weakness would be kind of coming in on a hook, essentially, taking a hard turn at the last minute to basically blow around a system that may be only pointed directly outward. So you have to look at kind of a range of velocities that your vehicle can attain.
And serpentines are a DoD recommended approach. They use them all the time at military bases for guard checks, that you're doing this so that you can't get going more than 10 or 15 miles an hour before you hit the barrier, because you're going to go through several barriers before you get there.
And sometimes that'll work if you have a point item that you're trying to protect. But if you have an entire perimeter to protect, there's only so much you can do, and you're going to have to map out all the different circumstances that are feasible in terms of that vehicle getting up to that speed.
Yeah, and my experience has been large boulders, concrete walls are much better visual deterrents than bollard, and I think they perform better. I'd be more comfortable on the other side of a concrete wall than I would be on a row of bollards, because they only offer point protection every 5 feet.
Even boulders you have to be careful with, because we had an instance here 2 blocks from my house where there was a boulder over 1,000 pounds that was run into by somebody who fell asleep and was going down a residential street close to 100 miles an hour. And guess what? That boulder went over a block and became its own kind of hazard.
And that's the equations that I see a lot missing is they'll say, look, I've got enough mass to equal the weight of the vehicle. Okay, but if the vehicle's going 60 miles an hour and it hits an object the same weight, they're both going 30.
Yeah.
Now it's inelastic, so that's not fully accurate, but since we're talking about static equations, well, how are you mitigating these things that are now rolling at 30? Well, I got twice the weight. Well, again, they're still moving. What's your slow down mechanism? And being immovable it's a tough course. And I think we're really handicapped by the fact that cars are so spongy compared to the buildings we normally design, that the two worlds, cause problems. And it's definitely overly conservative to treat them as rigid bodies that accelerate at a constant velocity or constant rate. Like I said, the math just makes my head hurt thinking about what you would have to do to model.
So what are we recommending here? That's I guess we're trying to take a broad brush here. What are we recommending?
You either design per AASHTO with the limitations that this is a good barrier, but it's not going to stop somebody with malicious intent.
Right.
You go to the DoD rated bollards because those will perform exactly how you want them to do. But then there's always a question. Is it a 50-ton? Is it a 60-ton vehicle? Is it a 30-ton vehicle? Is it 50 miles an hour? Is it 70? Because those are all things that play into effect. Understanding that it will perform within a certain criteria, but the penetration is going to kill anybody close. It's a tough sell that vehicle is going to incur 10 feet easily on the most stringent rated bollard. Or explain to the client that there may be less liability if you don't put a system in. Because sometimes we deal with that. You put a system in because you thought there was a threat and it didn't mitigate the threat, so you're liable for that. Whereas if you don't put the system in, you're not admitting that there's potential risk.
Oh, there's that, I guess.
It's a complicated environment. The trouble is the people who should be making the decisions aren't.
Yeah. And never let a client tell you what rating they need.
Yeah, that's not their place. They need to tell you the criteria they want to meet.
You tell them what asset they want to protect. And you don't let them choose the rating of the bollard any more than you let them choose the load factors that you design with.
Yeah, or the size of the foundation or
anything.
Yeah.
Right.
So you have to have that communication, and you need to do it up front when you're approached, and the trouble is there are those in our profession who are like, oh yeah, I can do that. No problem. I do it all the time. And yeah, because they don't know any better. They're not the professional, but the person they're selling their vaporware to that doesn't know any better. You just have to have that open communication system. We have clear guidelines, but here's what they do. If you're expecting to have a barrier that has 500 people walking into a mall and there not to be any collateral problems if somebody decides to skip that barrier, then you're opening yourself up because you're not explaining the limitations of the system. And that's what they expect. They think I put in a bollard and it's going to stop everything miraculously, and there's nothing that's going to fly in and hit my people that I'm trying to protect. And
right. So if you have a security booth that's 5 feet away, you did nothing for them.
Yep. Right. They need to be set back so that they don't get, incurred upon, as the DoD would word it. Well, awesome. I love bollards, and I think it's because I've seen so many bad designs that it's something I can get worked up and frustrated about.
Right. And we've seen them in use more than once. We've seen
function.
Yeah, we've seen them function and how they do all different types of systems, surprisingly.
Yeah. And if you haven't seen a crash test video, go just search K-rated bollard on YouTube and you'll get manufacturer after manufacturer that shows these trucks flying into bollards. And that's probably the best thing you can do for your client. Say, here's the rated bollard. Is it matching what you expected from performance? And I guarantee they'll say no. That truck went all the way in. Like, you're right, but the payload stayed out. The explosive device didn't get close enough to the structure to be a problem. Because that's the DoD threat. We want to stop explosive devices, not the vehicle itself, because they have people with machine guns to do that. So, all right, on to something fun. I enjoy this. So I think I mentioned in the first podcast that we would talk a lot about cars. It's just the way Tim and I are. I mean, I don't want to say I'm a car guy, but I'm an enthusiast of vehicles. I think they're fun. So I have a Mazda 3, 2007 Mazda 3, with 221,000 miles on it. And I recently replaced the motor. Actually, like 2 days ago, was finally finished. And today I got the air conditioner working with and some other final tweaks. I want to talk about the background of this vehicle because I spent about $1,000 on this motor, which is way more than the car's worth. But it's cheaper than a replacement vehicle, and I know that the vehicle's been maintained for at least the 100,000 miles that I've owned it. Tim knows the story of this Mazda 3 and why I have this Mazda 3. I have a Chevy 1500 truck, 2006. That's what I drive around all the time right now because the Mazda's been down for a year. But I got a job at Disneyland with Tim, but I was living in Phoenix. So Tim, what was my solution to that problem?
Well, you continued to live in Phoenix, and you only went home on weekends, and had a house in, well, two different places. One about, I don't know, 70 miles away.
Yeah,
Is that about right?
Oceanside.
And then one, yeah,
60,
for a while, and then also
Garden
one that
Grove.
was relatively closer for a while. But,
I rented rooms.
But just commuting on Friday afternoons, like I'm going home, I'm going back to, was it Chandler? Where was it?
It was Chandler. Yep. So we were just west of Phoenix, or east of Phoenix in the East Valley. So I had been driving around my Chevy 1500 for a few years, and my wife's got her car, and that was fine for commuting within Phoenix. As I started to run the numbers on gas to drive between Phoenix and Orange County, it became very apparent that I could pay for this Mazda 3, which I paid $3,200 for, within like 6 months, that the car would pay for itself just in fuel consumption. And so I was averaging over 1,000 miles a week on the car. I think that first year I put 60,000 miles. So I bought the car at 130-ish thousand miles, and the 18 months that I was commuting back and forth, I ended at about 210. I drove it around in Florida for a year when I moved out here, and then I threw a bearing in the motor. One day, I think the oil got a little low, and so the bearing went out, and I could hear it. I was in the middle of remodeling my house, and so the car sat, and it sat, knowing that I wanted to replace the motor because I have a kid who's getting ready to turn 16, and he's going to have to commute back and forth to college, and so he needs a car. And it's cheaper to drive. I'm paying more to drive my truck around, and to me, I want to use my truck on Saturdays to go to Home Depot, not drive to work. So about a month ago, I bought the motor finally because the house is done. I've got a buddy who's got a shop in his backyard with a lift, which makes all the difference. And he races cars, so it was very helpful to have somebody with that kind of knowledge. And I will turn wrench, but swapping a motor was scary to me. I thought there's no way this is going to work.
Yeah, that's major surgery.
I always knew there were lots of connectors and hoses and pipes in a car. Yeah. But when you start unhooking all of them, and even worse when you try and put them all back together, you're like, where does this one go? It doesn't line up with this connector. And I thought, and there's a connector over here. Like, is there supposed to be a cable in there? I don't remember pulling one out. So the conversion...
That's my phobia. It's that I'm going to forget where a couple of things went.
And there's all these brackets that bolt on just to hold like wires and cables in place. And so not all of those made it back on. But it probably took, between the two of us, 80 to 100 hours to accomplish this task. Right. And we did a conversion that's pretty common for people with Mazda 3s and even the 4-cylinder Mazda 6. And that is... It's basically a Ford motor commissioned by Mazda, and so if you look through the origin of these things, it's a 2.3 liter straight 4 motor that was the mainstay, and there was a generation difference between like 2004 and 2005, and mine was new enough that it helped with the conversion. There weren't quite as many anomalies. Well, the Ford 2.5 liter motor is the newer generation of this 2.3, and it's just a wider bore. Pretty much everything else about it's the same. So everything else, geometry is locked in. So I did the 2.5 conversion, gives you 20 more horsepower or something like that. But the big cell, it's a third the price to buy a Ford motor than it is to buy the Mazda branded motor.
That's so weird.
Well, because there's so many more, Fiestas and Focuses and Fusions that have this motor in it that they get wrecked. They get wrecked all the time. And
wait, so is it one of those? What do they call it? The Ford's fancy high efficiency engines. What are those called?
The EcoBoost.
Yeah, that.
No, it's a nothing fancy about it. Thankfully, that I think that helps. But I ended up getting it out of a Ford Fusion 2013, 2014 with 40,000 miles on it. So it's brand spanking new. And
what is it, 2 liters or something?
The 2.5 liter.
2.5.
Yeah, 2.5. And so we'll share a video of us turning the motor on for the first time. Yesterday, I think it was.
That's good size for a 4-cylinder engine.
Yes. Yeah. I mean, it's got like 180 horsepower, so it's not slouching for a vehicle that size.
Nope.
But it's interesting because you have all these sensors and things that you have to pull off the old motor and put them on the new motor. And sometimes there's 3 wires and you had 2, or there were 2 and you had 3. So basically the block was the Ford motor and almost all the components were pulled off the Mazda to make it happen. We had to switch oil pans because they're completely different shaped at the bottom. And other than a few minor bumps for sitting for a year, we ran the diagnostics and pulled the codes. And once he cleared all the old codes, it wasn't throwing anything new. It had 3 misfires out of 65,000. So I felt like that's pretty good batting average for a vehicle that old and, swapping in a new motor. One of the problems is the timing gear, or I guess the crankshaft position. See, I learned all these words. I learned what all these parts are now. The crankshaft position sensor is a gear with teeth on it, right? And there's an induction sensor that picks up which tooth it's on, how wide the gap is, so it knows where the crankshaft is. Well, rather than having that be a registered gear that fits on a registration mark, it's friction fit. So when you go to pull, and there are different sizes, so when you go to pull the old one on the new one, you have to make sure the cam is locked and doesn't move, and that you install it in perfectly the right orientation with relationship to that sensor. Otherwise, it'll be mislocated. Okay. So that was a hair-raising moment where we're like, did we do this right? Like, is this thing going to be sputtering because it's going to be firing at all the wrong times?
Yeah, and I mean, it's sensitive, that kind of thing.
Yeah. So, luckily we kind of logically figured it's variable timed, right? So the idea is that if it's off by a little, the variable timing should correct that because there's 2 position sensors.
Yeah.
And that one is locked in; it doesn't change. But I'm happy I drove it around today. I had to replace the temperature sensor on the engine because it wasn't faulty, but it had broken. It had pulled out of the bushing. The actual sensor piece had pulled out of the bushing that screws in. And so I replaced that just to make sure we were getting good engine temp. And then I had no air conditioner, which is a big deal in Florida. But it was just low on refrigerant. So we've topped that up and it seems to be working. But yeah, I'm hoping to get another, 40,000 miles on this motor. So I should get another 150,000 miles and maybe get this thing up to 400,000 miles on the body of the car. Unless my
and you said this is 2007.
Yep.
Okay.
So unless my 16-year-old decides to wreck the vehicle, it should last.
That's the inevitable demise of this car, right?
Yeah. Well, so right now it's not registered or not insured. It's registered, but I changed my insurance that it's not operable. So it's in my backyard, and my insurance agent was saying, even if you don't get it running, he's like, keep it insured, and we'll put the 16-year-old on there, even if he's not driving it, and it will be cheaper than any of your other cars. So it would have sat in blocks in the backyard at the very least until he was old enough to be on his own. Now I feel like I told my friend that helped me. I'm like, well, I guess it's time to do a kit car. Now that we've done this, and it's amazing, and it turned on the first time you turned the trigger and pulled the ignition and gave it a little gas and started right up. So
Yeah, it's amazing. I saw the video and I'm like, yay, I'm applauding. Good job.
It's yeah, it's fun stuff. I hope it works out. I haven't opened it up yet though. It's got a growlier, lower pitch roar to it than I think I remember the old motor having.
Yeah.
But it's also a manual transmission, which I enjoy, and so I'm thrilled to be able to have a roller skate, as Tim likes to call those small cars,
Yeah.
that sit lower to the ground and are kind of maneuverable.
I'm driving a manual also. My last car was a manual. I've had a lot of them. And
Yeah, and my truck's a manual, and I'm
Yeah.
not looking forward to teaching my son how to drive a manual, but I feel it's one of those things he needs to learn.
Well, just head over to the old abandoned mall parking lot and
Yeah, those are a lot of those these days, I suppose.
there are, aren't there? Driving schools.
Yes. Oh, well, thank you for joining us. Thank you, Tim. It's been a while since we've talked to each other this way. I hope everybody's having an enjoyable Thanksgiving holiday. We just finished that 2 days ago. So I hope everyone's well, and we will see you again here at the Rankled Engineer. Thank you.
Okay, ready?
Yep. Ha ha. Oh.